Network Dojo.
Here we're going to be talking about the major types of EAP methods that we would see in the exam, at least, as well as on the ICE server, as well as another protocol as well. So EAP, or these authentication protocols, are used to essentially more or less securely relay credentials that the server can then validate. And obviously when we send credentials to validate against, usually we want some sort of security around them, and that's where EAP comes into play. EAP, or Extensible Authentication Protocol, of many different flavors, allows us to exchange credentials, and there's some sort of a mechanism to protect them, so that if someone was, snooping in on the conversation, they couldn't just read plain text. Oh, there's the username, there's the password. So they have varying levels of security on this. Sometimes you might be able to see the username, but you can't see the password. Sometimes, it just depends on what's going on. But it's good to understand just kind of how the major EAP types work, what's required for them. Some of them use certificates, some of them do not. Some of them are username password, some of them are not. And so that, if we have any questions about these, that we kind of understand the components and hopefully can decipher the answers here. So the first EAP type that we're going to talk about is called LEAP. It's an old one, and it's the one that you're least likely to probably see in any modern network. It is a Cisco EAP-based protocol, so Cisco came up with this protocol, and you typically only see it on Cisco devices. So, any endpoints that Cisco makes oftentimes did support LEAP at one time. Supplicants by Cisco, like the Cisco AnyConnect client, supported it. You might see supplicants that support like CCX type functionality sometimes would support it, but it is a Cisco protocol. It uses username password for the credentials. There are no certificates involved, which made it a really easy thing to deploy, because there's always a sort of a barrier to entry when you start talking about certs, because it typically requires, okay, now we need to stand up a CA server and do this PKI thing. So we didn't have to mess with that, which made it very easy to deploy. It's very efficient, I guess. It doesn't take a whole lot of resources here. Unfortunately, it is broken in terms of security. What's broken about it is that I believe the username you can snoop in clear text. The password is hashed of some flavor, but it is subject to rainbow table attacks. So, some hash always reverses to some known password, and the mechanism for the hashing is broken in that, you can put in a password, force it through the hash, and it's always the same end result. And so what they do with these rainbow table attacks is they just take all the known common passwords you would ever want to have, put it through the hash. That creates what's called the rainbow table. Now they can snoop in on and see, okay, does it match any of these hashes? And then I know what the hash is reversed to. So unless you have a very complex password that wouldn't ever show up on any sort of a password table, it is definitely unsecure. ICE, while it does support it, it does not have support for it enabled by default. It is turned off by default, although you can easily turn it on. So that would be LEAP, Cisco proprietary. Well, it's a Cisco protocol. It's a username, password, credentials. There are no certificates involved. Unfortunately, it's very broken. Next up, EAP Fast. So this is another Cisco protocol. We have two basic Cisco protocols here. This is the second one. This is our first tunneled protocol. And so here's what a tunneled protocol, or I should say, the proper term here actually should have been a tunneling protocol. So tunnels, tunneled or tunneling protocols essentially have an outer they call it an outer method and an inner method. And here's the basic idea of this here. So let's say I want to send my username and password to be between my device number A here and my server. So I want to send my username and password information over here. And so there are a number of different protocols that we can use to send username, password information, but a lot of them are not very secure. And so while it's they very they're oftentimes they're older standards and they're very well adopted and very well supported, we wouldn't want to use them by themselves. And so what we do is we create a secure tunnel between the two devices. And so I can create this tunnel that encrypts everything within it. And then inside the tunnel, I can use a secondary method and pass the credentials inside the tunnel. And so technically the green one, the one that creates the tunnel, should be called the tunneling protocol, and the blue one that runs inside the tunnel would technically be the tunneled protocol. So apologize, I didn't think through my verbiage there. But there are essentially two protocols in play. The outer protocol to create the tunnel and the inner protocol that's actually used to exchange their credentials. And so in this scenario, EAP-Fast is used to create the tunnel. So it's called the outer protocol. And then within the tunnel, we have a number of different options. One of the common ones might be MSChap v2. And where MSChap v2 easily allows us to exchange credentials, especially in a Microsoft world, because that's the MS, Microsoft part of it. It by itself wouldn't be the best option, because I believe that would be easily crackable, if I understand it right. So we secure these less secure protocols with a more secure tunnel. So that's the tunneling process. So that, again, the outer method is used to create the tunnel. The inner method is used to actually exchange the credentials between the client and the server. So EAP-Fast would be the outer part of the tunnel, and so every outer method, part of the tunnel, has an inner method, the protocol used to exchange their credentials. And so the valid ones that we have, at least supporting on the ICE server, would be MSChap v2. So MS for Microsoft. I think CHAP is like Challenge Handshake Authentication Protocol or something like that. It's username, password. And we see this is like our go-to inner method for pretty much everything that we kind of do in the wireless world. All Microsoft devices support this by default. Pretty much every device just does MSChap v2 as sort of its de facto inner method for almost across the board, at least in all the work that I've done. But there are others. Another one would be EAP-GTC. That's another username password. You might also hear that in reference to like tokens. I think the GTC is like generic token card or something like that. I might be totally wrong on that one. But it's a username password option. But again, you also might see that in reference to tokens. And then we can actually do EAP-TLS. And so that's actually, rather than a username password, we send a certificate. But that's, again, these are much less likely things. MSChap v2 is by far the most common. EAP-GTC has some smaller use cases, and I've never heard of anyone actually using EAP-TLS inside of EAP-Fast. So those would be the valid inner methods for this. But more about EAP-Fast, because it's probably one of the more complex of our protocols that we have, or there's definitely a very unique part of it here, and that's with these PACs that it uses to build the outer tunnel. So PAC stands for Protected Authentication Credentials, or Protected Access Credentials, one of the two. But when we think about creating tunnels, a secure tunnel to encrypt the data from one side to the other, it pretty much, I don't know if there's another way, but the standard way of doing this is we get these shared keys. So both sides end up with these shared keys. One side encrypts it with the key. The other side has the same key so it can decrypt it properly. If you have the same key, if you know the key, you can decrypt it, and you can encrypt it so that the other side can decrypt it. And so that's pretty much how we do pretty much all forms of encryption here, reversible encryption that is. We get some sort of a shared key setup, but that's, how do we get that shared key between one end and the other without compromising our security? That's where these PACs come in. So a PAC is just a little file that gets provisioned down to the client, and it's generated by the server. So the server is the one that actually creates these PAC files, and then it gets it down to the client. And when the client and the server have, client has a PAC generated by the server, then they can, get these shared keys that can form this tunnel. And so normally it's an automatic push, although we can manually download it to a client offline if we really needed to, but normally it's just an automated push right from the client or server down to the client. And the information within the packs combined with a master key on the server allows for the tunnel creation, essentially. And so the pack becomes an important entity. So the server provisions packs down to the client, the pack matches up to the server, they can use this information to create our secured tunnel. And so when we talk about EFAST, there's technically 3 different phases of authentication, I guess, that might be worth knowing. So the first time that a client connects up to a WLAN that leverages a specific radius server and they want to use EFAST, the client won't have a pack from that server unless there was some sort of a manual provision beforehand, but let's assume that that's not the case. So I'm a client, you're the radius server, I want to authenticate up to you. I've never authenticated up to you before. So I do not have a pack from you. I need to get that. Otherwise, we can't do this process. So the first time that I connect, we go into phase 0. So what ends up happening is you actually, very early into the process, you actually send an identifying piece of information to me called your authority ID. And I take a look in my pack repository and I'm like, okay, do I have a pack signed by you based off of your authority ID? And the answer is no, I don't. And so I say, okay, we're going to move into phase 0. So we hit phase 0. We have a sort of a less secure way of creating one of these tunnels. I authenticate myself to you as long as I pass authentication. You send me a pack. And then actually at the end of that, now that I have a pack from you, we actually stop and tear down the entire authentication. So at the end of the pack provisioning process, the server, you say, you're rejected. Let's just kick you off and then we're going to start fresh now that you have a pack. Okay, so the end of every pack provisioning process of phase 0 ends in the client getting rejected. Okay, I try to connect again. You send your authority ID. I have a pack from you. Let's move to phase 1. So once I have a pack, we start in phase 1. We create the tunnel. We converse based off the information in the pack and the information that you have with your master key. We form this EFAST tunnel. Now we move to phase 2 where we use the inner method, probably MS Chat v2. I tell you my deepest, darkest secrets, my username and password. You check to see if those are correct. If they are, you probably permit me on the network, and then I'm up and running. So that's the basic process with EFAST. That's how packs come into play, or the use case for what packs are. So there are no certificates involved in this. We use packs to create the secure outer tunnel. It is a tunneling protocol where there's an outer method and an inner method. EFAST is the outer method. It's a Cisco protocol. And then we use more of a standard inner method like MS Chat v2, EAP GTC, technically UTLS as well. And that's where we actually exchange the credentials. Okay, PEEP. One that we're all probably very familiar with. We've all used it most likely at some point. This is more of an open protocol. It's supported pretty much on every single kind of device that wants to use EAP. This is another tunneling protocol where we have this inner and outer method. So again, PEEP would be the outer method. That's what we use to form the secured tunnel. And then within PEEP, we would use an inner method to exchange credentials. We see the same list there. MS Chat v2, which again is pretty much the de facto one that we use for most everything. EAP GTC, EAP TLS. Now, this is the first EAP type where we leverage a certificate on the server. So PEEP relies on having a server certificate. The clients do not need a certificate, but the server does. And so very early into the PEEP process, the server sends its certificate down to the client as a part of building this protected tunnel. Now the client has the option to validate the server certificate. It doesn't have to. This is completely dependent on how the client supplicant is configured. There's usually a checkbox that says validate or not the server certificate. If we don't, we'll take any server cert. Doesn't matter who it's from. But if we are validating the server certificate, which is always recommended to prevent against, talking to a rogue radius server, maybe someone's got a honeypot AP out there You connect to that. It's got a little radius server stood up on it. And it sort of, sends down its server cert, hoping that you're going to send it your username and password. Well, hopefully they wouldn't have a certificate that you trust. Hence, you would stop before you even send it the username and password. So that's why we would choose to validate a server certificate. So if we're going to validate it, I guess the question becomes then, how do we validate a certificate? So we do this by checking to see if the server cert is signed by a certificate authority that we trust as a client. If it is, we trust it, and we can actually go one step more. Not only is it signed by CA that we trust, but we can even have more stringent controls on it. It actually has to be named this in the certificate, or maybe it ends in a certain suffix like, all my certs end in networkdojo.com or something like that. And so, yeah, there might be different radius servers, x.networkdojo.com. I'll trust the networkdojo.com part. Or it has to be this particular server, because you can play it in a number of different ways. But by and large, we're mainly seeing is the server cert signed by a certificate authority that we trust. If the answer is yes, we usually trust the cert, and then we'll move forward with the authentication, build that tunnel, and I'll send my username and password using the inner method. Now, what if that fails? What if I have an error where I don't trust the cert sent by my server? What can I do in that type of a situation? Well, a few different ways. Number one, we could just turn off validation. The client could just not care who the server is and just ignore that part of it. Just skip the validation altogether. Number two, we could install a new server cert signed by a trusted CA. So if the cert on there, maybe it's a self-signed cert on that server. We're not going to trust the self-signed cert by default for sure. So we could get a CA cert, a CA signed cert signed by a certificate authority that we trust, either our own internal CA, or we could go out to like a VeriSign or a GoDaddy or one of the many public CA providers out there that everyone sort of trusts by default. Whatever it takes to get a trusted cert installed on the server. Or we could install the CA cert for the server on the client. So maybe the client, there is a CA signed cert on the server. It's just our client doesn't have the CA cert trusted in its repository. And so maybe we need to do that so that the client can properly validate the server cert. So those are kind of the main things that we would use to fix it if our validations are failing. And then finally, for what we'll talk about in terms of EAP methods, we're going to talk about EAP TLS. This is another open standard protocol. It's used and valid against lots of different types of clients. This is unique in that it leverages both a server cert as well as a client certificate. This is the only cert type that we really talk about in common use where the client doesn't send a username and password to be validated. Its credentials are its certificate. And so it sends its certificate up to the server, and the server needs to validate that. Now, since we do use a server cert, clients, very much like on the PEEP world, can optionally validate that server certificate. Same exact process that we talked about before. But the server must validate the client cert. The client doesn't have to validate the server cert, but the server absolutely does need to validate the client cert because those are the credentials. It's not a username and password, it's a cert. And that means that the server needs to have the client certificate CA server installed as a trusted certificate. So let's take a look at some certs so you can kind of see, what does one look like if you haven't really played around with them before. So this is a Windows 7 VM here, and I've got a number of certificates installed. And so these would be user certificates. So certificates sort of attached to a user account as opposed to maybe a machine account or something like that. And so, for instance, if I go into this admin certificate, we're going to start to see a few things about it. First and foremost, there is a validity date. There's a date when it starts being valid, and there's a date when it expires. And so certs always have a limited lifetime to them. This one happens to be a very long one, just to keep me from having to re-up my certs very often. So this one's good all the way through the year 2026. Cool. We can see who created this certificate. That's the certificate authority, or CA server. The CA is the server that actually creates and signs certificates that get used by servers and that get used by clients. So it is the one that creates all the certificates, and that's what we're really validating against. When I say, is it signed by a CA that we trust? Do I trust this certificate authority? So in this case, my certificate authority is named Network Dojo-Win12-CA. We can see it was issued to a user called admin. And it's useful for proving my identity. I can protect email messages, and I can encrypt data on a hard drive. All certificates have uses that they are valid for. And I can't use this, for instance, I can't take this cert and install it on a web server and be the cert for an HTTPS page, because that's not on the list here. So every cert, when it gets created, gets assigned certain use cases that it can be valid for, and I can't use it for anything besides that. And then I can go into the details and see even more information about this certificate. Not every last piece of information is important, but we see, what was the sort of hashing algorithm used to create this that gives certain levels of security to it. Some certain things maybe require certain hashing algorithms. Again, we see who issued the certificate. CM means common name, which we'll see it in a different part here. Again, when it starts being valid, when it expires. This is actually in relation to an Active Directory user. And so we sort of see more of a fully qualified path to it. So my common name is admin, which is actually in a folder called users, which is in the domain networkdojo.local. And so we see sort of this pathing in the subject. Try to find some other information here. Again, we see some information about the server that created this, the usage. Those were those use cases that we talked about. So everything that we saw on the first page shows up in the details here. Subject alternative name is another sort of place where you can put who the certificate is valid for. So this one is it's just in a different format, admin at networkdojo.local, as opposed to just plain admin. So sometimes certs can have sort of different usernames or names attached to them, host names. And then there's a sort of thumbprint. And if we look at the certification path, we can see, okay, who is this? Again, another place where we can see who the CA is that actually signed this. And sometimes you'll actually have tiers of CAs where you'll have like a top level CA, especially in larger PKI deployments. You'll have this top level CA, and then it'll have called subordinate CAs that are the ones that actually provision the certs out to it. And sometimes those subordinate CAs come and go, but the top level CA sort of stays forever, kind of a deal. And so you might see a couple of, entries, a couple of hops in the path here. But this tells you, okay, what's the path of the CA structure that created the certificate? So for me, I just have one. It's just a single tiered CA created this admin certificate. So I know who signed and created this certificate. So if I want to know if this certificate is actually legit, I can check it against this CA. That's how we validate certificates. Okay, this certificate says it's signed by networkdojo.win12-CA. Is it really? And do I even trust this CA? So, those are a couple of questions that we ask ourselves when we want to figure out if we want to trust a certificate. And like when the client, let's talk about that. So let's say that, when my client, I configure it to validate the server certificate. And so my ICE server will have a server certificate installed. So for instance, this is the cert that I use during EAP authentications. So during PEEP, during EAP TLS, when I send the server cert down from the ICE server, which we're looking at ICE right now, this is the server cert that I send down to the client, and the client can validate it. And we can see, oh, well, this server cert is actually issued by that same CA. It's issued by networkdojo.win12-CA. And so if I trust this CA, this certificate authority, I will trust this server cert. How do I know if I trust it? Well, let's go to the client. There is a trusted root certification authorities group that has a big old list. These are all the CAs that I trust as a client. And most of these are just pre-installed. They're like public CAs that, all the major websites out in the world, public websites out in the world would use certificates signed by these CAs. So again, there's like the GoDaddies, there's the DigiCerts, there's Thought, VeriSign, all these ones out there that we entrust by default. But on top of that, I should have Network Dojo-Win12-CA. So I do trust certs from Network Dojo-Win12-CA. So if someone sends a cert to me and I want to see, do I trust it? Yeah, I will trust it, because I have that CA's cert installed in my trusted list, my list of trusted providers. And on the ICE server, it's the same thing. When the ICE server needs to validate a client cert during EAP TLS, ICE has a list of trusted certificates. And so if the client sends a cert trusted by a server on this list, as long as it's checked for endpoints here, for instance, my Network Dojo CA, which, surprise, surprise, is Network Dojo-Win12-CA, I'm going to trust any certificates signed by this cert for EAP TLS authentications. And so we use this to validate all of our certificates. And not only do we, just look for, oh, well, yeah, it says it's signed by Network Dojo-Win12-CA, that's good enough for me. We can actually check if it for real is, or did someone just spoof it? Because I can stand up a CA server and have it say anything that I want it to, right? Doesn't mean that they should trust me. Well, when I install the CA's public cert, which is what I install when in here, any certificate signed by this CA has that little thumbprint in it. And we can validate it, is this legit signed by this cert? Because this certificate can validate that thumbprint. That thumbprint can only be validated by the real CA. If I stood up a GoDaddy server and signed a cert that says, hey, this is from GoDaddy, well, people have GoDaddy's real CA cert in their list of trusted certificate authorities. And so when my thumbprint won't match up to the real CA server cert. And so they'll know, oh, this is phony. I'm not going to trust it. So that's how we validate certificates, is by installing the CA cert of the server that signed the cert into some form of a list of trusted list. And we have this on the server side. We have this on the client side as well. And that's how we're going to validate everything. So just a small little crash course in certificates there. Okay, one other protocol that we're going to talk about, and we'll end it here, and this is not an EAP protocol. Notice it doesn't have the word EAP in it. And that means that we would not use this for 802.1x authentications. 802.1x requires EAP. But we have other authentication protocols that we can use when we're not doing an 802.1x authentication. So what are those use cases in our wireless world? MAC filtering. There's no EAP authentication. There's no username password negotiation from the client for that. So MAC filtering it uses this protocol. Management-based authentications. So if I use Radius to authenticate my AirOS management users, or validate, I'm going to SSH into an autonomous AP and send that up against a Radius server. Management-based authentications use PAP-ASCII by default. WebAuth. If I have a local WebAuth WLAN on my controller and I want to validate the credentials against Radius, again, it's not an 802.1x network, so it sends that username password up to ICE using PAP-ASCII. So if it's not 802.1x, this is really what we use for everything by default in our worlds, at least. It is an open standard protocol. The username, it's username password. So we send a username, we send a password. Unfortunately, it is plain text, I believe. So this is in 0 ways secure. So we're okay on normally. We're okay in the wireless world. Like, again, think about that guest WLAN. While, yes, we're putting in username passwords, and yes, PAP-ASCII itself does not protect our credentials, where are we putting the credentials in? We're putting it in an HTTPS web page, right? So even if these were like our credentials, our real credentials, it's in an HTTPS page. Anyone that snoops the traffic has to break into HTTPS tunneled communications, which there's no easy way to do that. At least not that I know of. Hopefully there's no easy way to do that. Otherwise, every banking transaction would be screwed. So we're okay there. Where you run into problems is if someone can snoop into it on the wired network. So this is the conversation from the controller to the server, or from an autonomous AP to the server on the wired network. And so the only way to get at this stuff would be wired snooping. We can't see this on the wireless, so we're okay there. We're safe, having open SSIDs and things like that. But PAP ASCII, extremely simplistic, used for pretty much anything that's not AO2.1x in the wireless world for sure. Username, password, open standard, but not secured. So we'll wrap it up there. There are other EAP methods and there's other authentication methods that are referenced in different places, but we never really see them used anywhere. And so we'll end the conversation, I guess, at that.